1 tuples of vertices. Okay, I mean, it's not all possible, d plus 1 tuples, but in this sense, it's like a graph product, and you see how it's a lifting question, because what do you want to prove now? Or what do we know how to prove? We know that if you have a coloring here that violates some fraction of the edges, then no matter how you color G1, it will violate a larger fraction of the edges. Okay. So what can we prove? So we claim, or I'm not really going to prove it, but if the uncolored, that's a good way to call it. I usually call it ansat, so let me just stay with ansat. The ansat of G is at least epsilon. So what do I mean by this? G, remember, was just a coloring instance. You color it with 3 colors. And then there's some fraction of the edges that are unsatisfied. They're monochromatic. They're not supposed to be. So this is the ansat value. It's the fraction of monochromatic edges, no matter how you color G. It's like the minimal fraction. Then the ansat of G1 will be bigger than 2 epsilon. So this is true if you take the neighborhoods to be large enough. But, okay, so it's qualitatively true. All right, so this is like what we think of as gap amplification. Really, for gap amplification, you also need to have the converse, which is obviously true here, that if the ansat of G is 0, meaning this means that G is 3 colorable, then the ansat of G1 is also 0, meaning, you know, if there's a perfectly consistent 3 coloring here, you can just be perfectly faithful to it when you define the local view colorings, and then everything will work. Okay? So in that sense, you know, then if you define this perfectly consistent local collection of local views, this collection can be lifted perfectly back. Okay? So you see how from a global thing you break it up into a bunch of local views, and you want to also show that if you have a bunch of local views, you can lift them back into a global thing. And so the point is that you can prove that you can do this lifting even when there's some not perfect consistency, but only mostly consistent. So this is really what this statement says. The statement says, look, if the ansat value here, so okay, so how do we prove? Proof of claim. It's not really a proof, it's just the idea, proof idea. So given some coloring of G1 that has small ansat value, so if we have a coloring of G1, so remember, this coloring, it's not a 3 coloring, it's like a 3 to the D roughly colors. 3 to the D plus 1 minus something. If you have such a coloring of G1 with small ansat, smaller than 2 epsilon, so it's the contrapositive. I prove that if ansat is smaller than 2 epsilon, then the ansat here should be smaller than epsilon. And how do we do that? So now we are given a collection of colors. It's like a collection of local views here. And the ansat is small, so it means that most of the pairs are consistent with each other. That's exactly what it means. So it's exactly the setting we talked about. It's a setting where we have local consistency between pairs. And now we prove that you can lift it back up into a global consistency with some underlying coloring. And because in each local view there were no monochromatic edges, it will also show that somehow there are no monochromatic edges here, and that is a contradiction. So then we can lift it to coloring of G with a ansat smaller than epsilon. It's a contradiction. A contradiction. Okay, so that's all I want to say about this. Just to kind of show how the lifting is inside this proof. And so then what you need to do, you move from ansat being bigger than epsilon to ansat being bigger than 2 epsilon. So the way the proof, how does the full proof go? You started with a graph G that all you know is that it's either 3-colorable or not. So either the ansat value is 0, or the ansat value is non-zero. At least one edge is unhappy, so it's at least 1 over the number of edges. You move to G1, it's now at least 2 over the number of edges. It's 2 over E as a fraction. It doesn't have anything to do with the number of edges in G1. It was 1 over M, now it's 2 over M. Here it was 2 over M, now it's 4 over M. And you keep going until you get to a constant. This is how the proof goes. And one thing you might justifiably worry about is that when you moved from here to here, you're no longer in a 3-colorable situation. So you can't really repeat this step again. So you need to, from G1, move back to some G1 prime that is a 3-coloring instance without losing the ansat value. So this is what we call the alphabet reduction. It's like reducing the number of colors. This is what this means. It's a non-trivial step, which is kind of not in the scope of this lecture. Okay. So so this kind of repeated lifting from local views to global views amplifies the gap from we started with a gap of 1 versus 1 minus 1 over E. When I say a gap, what I mean is that we are given a graph G. We don't know, even though we see the graph, but in polynomial time we can't tell whether it's perfectly 3-colorable or you can only color this fraction of edges correctly. You color the vertices, but this fraction of edges are happy. Okay, so what this theorem says is that you can amplify to a gap of 1 versus 1 minus epsilon 0 for some constant, absolute constant. Now, so this is the PCP theorem, it's called the PCP theorem. It's equivalent to the PCP theorem. And then you can also amplify further, or you can wonder whether you can amplify further to 1 versus delta for any constant delta. Okay, and the answer is that yes, you can do this by another graph product, by a direct product, aka parallel repetition. Okay, so this is my next next thing I want to talk about. So if we have time at the end, I want to also tell you about some interesting open questions, wondering whether you can continue doing this kind of trick more times and get this kind of amplification. I mean, why stop at 1 minus epsilon 0? What happens if you just keep going with this kind of trick? In some sense, it's much more efficient than direct product because, see, the number of vertices stayed, it was n, it stayed n. And then it stayed n, and then it stayed n. So, I mean, the alphabet reduction does blow it up by some constant factor, but it's kind of a very efficient transformation. Whereas parallel repetition or direct product, it's the usual graph product. You have n vertices, now you have n squared. You do it again, you have n to the 4. So it's very inefficient. So it's a kind of it's a very important question. It has to do with like the exponential time hardness of various questions, whether you can do this kind of step to get to amplification 1 versus delta. Okay, so maybe we get to that at the end, or maybe not. Okay. So now I want to move to talk about parallel repetition. So this is also a direct product of graphs and of games. Graphs and games. So, maybe just to say, for those of you who have not heard of this a lot, the reason we care about this 1 versus delta, and also the reason why the PCP theorem kind of is very important is because it has a lot of applications to, as I said, the hardness of approximation. And really what has been very useful for hardness of approximation is this version, what we sometimes call the strong PCP theorem, okay, where the gap is between 1 and 0, or almost 0. Okay, because this kind of, okay, maybe we'll say it later. So this theorem is much more useful in some sense than this. Okay. So how to get one to the other? So we had our graph G. Let's draw it again. Yeah. Okay. So I have my graph G. I'm thinking of it now as a three-colorable graph, where I know that either G is three-colorable, or the ansat of G is at least epsilon 0, meaning every coloring will falsify at least epsilon fraction of the edges. Okay, now I'm thinking of this edge versus vertex game. So unfortunately, in my first lecture when I talked about a three-sat and the clause versus variable game. This is exactly the same, and I should have used this terminology then, but now I'm moving to this terminology. So what I want to define now is what we call a two-player game. One player is called the edge player. One player is called the vertex player. A two-player game that perfectly corresponds to this graph. Okay, and so one player is the referee selects a random edge, selects that edge to the edge player, and he selects one vertex in this edge. Selects one vertex in this edge and sends it to the vertex player. Okay, and then the edge player needs to give back an answer saying, I'm coloring this edge with blue and green, and the vertex player needs to say, I'm coloring this vertex with green. Okay, so there's a referee. He sends a question to the edge player, and he sends a vertex to the vertex player, and then the vertex player returns a number in 1, 2, and 3. And the edge player returns a number in 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. So it's some 6 numbers that he can say. Okay. And of course the referee will accept if consistent. So now obviously if G is three-colorable, there's a perfect strategy for the edge and vertex players. They can win all the time. And if G is not three-colorable, then there is no perfect strategy. They will always lose with probability at least epsilon 0 over 2. To see this, think of any strategy they choose. So the vertex player has some strategy. Think of it as a coloring. Okay? And now, this coloring violates a bunch of edges. So what is the edge player going to do? Well, for any edge that's not violated, the edge player might as well say whatever is consistent. For any edge that's violated, well, it needs to cheat on at least one of the sides, and there's probability half to be caught. So epsilon 0 over 2. Okay, so we already kind of proved now that it's NP hard to decide if the value of the game, I didn't formally define what this is, but I hope you understand. It's, what is the success probability maximizing over all possible strategies? Okay? If the value of a game is 1, or at most 1 minus epsilon 0 over 2. Okay. So, actually I have the setup. So far this is not parallel repetition. Okay. Actually, what I'm going to talk about now is a symmetrized version of this game. Okay, just to tell you kind of the terminology, you notice that this game is what we call a projection game because the value of the answer of the edge player determines the only possible answer for the vertex player. So if the edge player answered 1, 2, and this is the question V, then this guy better answer 2, otherwise he will lose. Okay, so once the edge player answered, the vertex player is answer, there's only one possible answer. This is called a projection game. So sometimes you hear it. But I want to talk about the symmetrized variant, which is like, sometimes we call it a collision game, or a symmetrized projection game. Okay, so what is that? Here, there are two edge players. Okay, basically, instead of having an edge and a vertex, what you do is you select a random vertex. You, I mean the referee. What the referee does really defines the game. So the referee selects a random vertex, and then he selects a neighbor at random, and then independently another neighbor at random. Might be the same, might be a different one. Just two edges incident on the same vertex. So I'm not going to define it in general. You can generalize it easily. Just define the symmetrized game for this game. So referee selects a random vertex in G, in the vertices of G, and then in two neighbors U and U prime of V independently. And then he sends UV to the first edge player, to edge 1, and U prime V to edge 2. So these are my names for the two players. Two players are symmetrized. They have the same thing. And actually, I don't view it anymore as a two-player game. I view it as a coloring problem, what we call a CSP, a constraint problem, where really I don't need to think of it this way. The way I think of it is you just draw a new graph. What is this graph? You have a vertex for every edge. Maybe you are familiar with these graphs. You convert every edge to a vertex. This is just a line graph. So here is E prime, and you put an edge between E and E prime if they share a vertex. This is just the line graph. So this is the line graph of G. Okay, but it's no longer a coloring in the classical sense. It's another coloring problem. I want to say. I want to call it another coloring problem, or we sometimes call it a CSP or a constraint graph. There is some constraint between these edges. The constraints say, look, I am interested in a 6 coloring of this graph because remember the edge player has 6 possible answers, all the pairs of numbers that are not the same. So, I want a 6 coloring. It's the what?
It's a directed line.
Is it?
No, because UV and VU don't think about them as
No, I do.
Oh, you
Don't I? Yeah, I do. It's not directed. No, not directed. So I want a 6 coloring of this graph, and these are, and I'm enforcing these are consistency constraints. It's the natural thing, if these two edges share a vertex V, then their colors should say the same thing about V. Okay, so here, this is my new graph. You can call it G symmetrized. Okay, it's also like the adjacency matrix can be written as like a. Okay, never mind. All right. So it turns out that I'm not going to go into this. It's easy to see that the value of this graph, there's a perfect coloring if there were a perfect coloring, if and only if, and if there was some epsilon 0 lower bounding the answer value, then there's some other epsilon 0 bounding this. So we might as well just be talking about this graph all along. Okay, now interestingly, this is a nice analytical way to express what it means for the success, what it means to have a strategy for this game, and a coloring, and how do you measure how successful it is. So until now, when we talked about coloring, I only allowed assigning a vertex one color, 1 out of 6 possibilities. It's useful to also think of randomized assignments where you allow a distribution. Maybe it doesn't seem very meaningful now, but you will see later when we talk about parallel repetition. So maybe I should first talk about parallel repetition. Yeah, let me do that. Okay, forget about this analytical thing. Let's do parallel. What is now the parallel repeated game? Yeah. Of a two-player game. So this is kind of in my head, when I say two-player game, I'm thinking of this situation where I have these 3 objects, a referee, a player 1, and a player 2. Okay, these are it's a two-prover game, not two-player. I should call it prover. Two-prover. And then this is prover 1. And this is prover 2. They want to prove to me that the graph is 3-colorable, but they can't. Okay, so what is parallel repetition? Do it twice, right? So you select the referee. Really what the referee is doing is specifying some distribution over pairs of questions, an edge and a vertex. So that's a question pair. Another referee can choose 2 question pairs independently at random. So it chooses some edge and a vertex, and then some other edge and a vertex. These are 2 question pairs. You can do it k times with a k parallel repetition. And then it's parallel, so the referee sends all of the edges to the edge player and all of the vertices to the vertex player. In general, he selects a question pair and then another question pair, and he sends both, the question pair belonging to the first player here and the question pair belonging to the second player here. And they answer 2 answers. And we had this example with the bit, flipping the bit. I will remind you, we thought of this game where the referee flips a coin, tells it to Alice, doesn't tell anything to Bob, and Bob needs to guess. And then we said he also does the same, but tells to Bob, and Alice needs to guess. And then you say, let's do it in parallel. The referee flips 2 coins, tells 1 coin to Alice, 1 coin to Bob, and they each need to guess what the other guy has. And even though playing 1 time, the value is exactly 1/2, what can you do? You just guess. Playing this parallel repeated game, playing it twice, they can do better than a half. Sorry, they can do better than a quarter. They can do a half. Okay, so it's very, very weird. A priori, you would think that if you play the game twice and you had some probability of acceptance, it just goes down exponentially. But this kind of very simple example shows that's not the case. So the question is, what happens to this value? Does the value go down? In this example, after 2 iterations, it doesn't go down at all. But it turns out that if you continue, it does go down. This is the parallel repetition theorem. So whereas the value of the repeated game goes down like some 1 minus epsilon to the n, assuming that the value of a single game was less than 1 minus epsilon. So I should have written it the opposite. If you have a game with value bounded away from 1, then the n repetition, should use k, the k repetition goes down exponentially. It's not with the same epsilon, it's some other epsilon. Maybe it's epsilon cubed or something. So the way I want to describe it for collision games, it's like a graph product. What is the graph product? So let's return to our line graph. Where is it? It's this. So now, this is our game. Before we repeat it, it's just one game. What is it? It's derived from this vertex edge game. You have 2 edges that share a vertex, and you want to check that they're consistent. So what would be a repetition? It's just a graph product where now your new vertices are for pairs of edges. So you have E1, E2 connected to E1 prime, E2 prime. If E1 was connected to E1 prime and E2 was connected to E2 prime, and you check inconsistencies if both coordinates are consistent. So I will write it formally. So the let the edge versus edge game graph. Okay, the game. So when I say game here, what I mean, so I'm not giving very formal definitions. I hope you understand because I'm giving a very concrete example. So this is a game. How is it a game? Well, it's a graph, and also there are some underlying 6 colors that I'm thinking about, and there are all these, each edge is decorated by some kind of constraint saying which pairs of colors are legal. So this to me will be a symmetrized game, a game. So okay, so let H be this game. So we define H times H, okay? How? So this is really, the reason I wrote tensor, it's because it's the tensor. So the adjacency matrix of this, so the vertices are the vertices of this squared, and the edges are defined by the tensor of the adjacency matrices, meaning, okay, so it's the vertex set is VH squared, and the edge set is E of H tensor E of H. Whatever that means. Hopefully you understand that I mean this as tensor of adjacency matrices. But let's be more formal. It's all the pairs of, oh, okay, so E1, E2, and E1 prime, E2 prime. Okay, so it's a set, and these are undirected edges, such that E1 prime is an edge, and also E2 prime was an edge. So I'm sorry that I used the letter E here to denote a vertex, but okay, this is how it came. It was a line graph. You're more used to seeing it's exactly the graph product I described also in my first lecture. So you just a pair of vertices here, a tuple of 2 vertices here is a vertex. It's connected to this tuple if every coordinate has an edge. Okay, and I want it to be a game, so I also need to describe the constraints. So remember, we had consistency constraints between this pair and between this pair, so this is going to be my consistency constraint. Good. So this is really the graph product corresponding to the game. And now the question is, how well can we 36 color H squared? Okay, so now, in the semantics of a game, the referee sends 2 questions to the edge player, and it expects 2 answers. So it's one answer is a number from 1 to 6, another answer is another number from 1 to 6. So it's really 36 different answers. So I'm allowing 36 colors, more colors, but I'm expecting still, even though there's more colors, I'm expecting that you can only satisfy a smaller fraction of the edges, corresponding to, the referee will catch you more often. Okay, so the theorem, and this is this theorem by Ranu. It's called the parallel position theorem. It's I think I wrote it here. Here. It says that you can do it very well. So like the ansat of H to the K, is what I wrote there, 1 minus epsilon prime to the K, assuming, okay, the ansat is 1 minus this. The ansat is actually the fraction that you violate. So this is the fraction you can satisfy. It goes to 0. Sorry, the ansat goes to 1. Almost everything will be violated. Okay, you guys are very quiet, so I'm worried. At least. So it's like almost 1. So how about questions? No? Right, so Tali asked if this is also through this lifting. The answer is yes. So to give an answer, you need to ask yourself, okay, so how do we prove these things? How did Run prove his theorem? So the answer is not exactly a yes. Conceptually, the answer is yes. But really, these things are a bit different. So let me talk about that. Yeah. Okay. So maybe it's even good to not think of just a product of two h's, but like a product of k of them. And then, what is the picture that I have in mind? Maybe I have it here. No, okay. So I had my original h, and now I look at h to the k, so my new vertices are k tuples of vertices in h. Okay, so from h to the k. Right, so I have my h. And now for every k tuple, and so on, for every k tuple of vertices in h to the k has a vertex. Right, so it's a bigger graph. It has n to the k more vertices, and really every vertex here corresponds to some k tuple of vertices. So this is very much identical to the lifting question that we had 2 days ago, where you have for every k tuple you have something, and now the difference is that now it's not that you connect two things if they overlap or if they're consistent, but rather you connect two subsets. If this subset of k vertices had edges to this subset, then you would connect these two vertices. Okay, so this is then you have an edge here. Okay, so it's different, and so yeah, it doesn't have to be a matching. It has to be at least a matching. So there must be an edge from here to here and an edge from here to here. There might be other edges, but don't care about them. Now, interestingly, but I won't go into it because I kind of had experience in previous talks that this is confusing, so I won't do it. You can define a specific simple game, like the edge vertex game, even more trivial game, which we call the confuse and compare game, such that the value of the confuse and compare game is exact, or like the game itself is exactly like the lifting question. Yeah, and then you can say, if the value of this game is epsilon, then the strategy must be a direct product. Okay, so it's good that I forgot to say this before. Okay. Even in this setting, it's always true that if you have a strategy for H, taking the kind of direct product strategy is some strategy for H to the K. I mean, you can always answer a K tuple of questions by answering each question separately. So this is always something that the provers can do. Okay? And this strategy will indeed achieve a value that's exactly 1 minus epsilon to the K. Okay? The point in this example with the coins and in other examples is that miraculously, this is not the best thing they can do. They're not always best to do a direct product strategy. Okay, this is via direct product strategy. So when you try to prove this, you need to, one kind of approach is to say, look, okay, they might not be exactly direct product, but I will show that essentially they're bound to be some kind of direct product. And this is in the spirit of proving a lifting theorem, showing that no matter what they do, there is some underlying strategy for the original game. Okay, but it turns out that these questions are not identical and similar techniques, but not identical. Okay, so now I want to give some kind of sketch of how to prove this. Yeah. So what should I keep? I guess so.
lifting is possible or not possible, and you couldn't know, or
All right. So in the parallel repetition setting, you move from H to H to the K. You have, for every K tuple of questions, you have a question. So this corresponds to my set, the lifting in the case of N choose K, the full N choose K. You can also say, look, okay, you have this graph. You can also focus on some small subgraph of this, consisting of a small subset of these vertices, hoping that there are still many edges inside this graph. And this corresponds to focusing on I had my A where it was supposed to be a smaller subset of N choose K. And in fact, what I showed you in the beginning of today, with these neighborhoods of vertices, there were K tuples, but instead of having N to the K tuples, I only had N K tuples. So it was exactly this situation, where you actually focus on a very tiny subset of H to the K, of size N. This is N to the K. This is size N. And you still show some kind of amplification. Okay, so sometimes we call it de-randomized parallel repetition. In parallel repetition, you kind of select each edge in the K tuple at random, independently. And in this version, it's not independent. It's recycling the randomness. So it's called de-randomized parallel repetition. And there are a lot of open questions about it. Relating to open questions that I described on lifting. Really, the only reason I framed those questions on lifting is that it's a combinatorial question as opposed to computational. So it looks like easier to prove lower bounds on that. So it kind of is simpler to think about. So I don't have that much time, but I think I will manage to do something. All right, so I want to prove parallel repetition. I'll keep the picture of the symmetrized game. So the theorem is this. Let G and H be. So now G is not the G from which H came. There are two. Okay, let me call them. Yeah, G and H be two collision games. You can think of G being equal to H. So it's just the same game twice. And now I'm taking the product of them. So earlier I just defined H times H, but you can really do H1 times H2, right? You just like graph products. You take V1 times V2, and here you take E1 times E2. Everything works. So two collision games. And you want to prove that the value of this game, G times H, is smaller than, well, okay, so this is false. This is I would call it idealized product theorem. And it's false. But it turns out that you can prove it for some other number, which let's call it val plus, some kind of relaxation of the value of a game. Okay? So this is the theorem I want to sketch. Is for?
G and H?
No, so val plus of G. So it turns out that you can define some kind of relaxation of the value of a game for a given graph G. It doesn't have to do with H at all. Just you have a graph, there's always a way to relax the value in a way that makes this inequality hold. And it's similar to a lot of things that we have seen, like the Lova's theta function, which is some kind of relaxation of optimization problem. And we do this often. So this is another kind of relaxation of the value of the game. Okay, so to define it, I first want to tell you how to think of the value of the game. And then we will define it. And then we will prove the second theorem. Maybe I should call it a lemma. Okay, and this is like a Chigger inequality for games, for collision games, which says that if the value of g is bounded away from 1, say 1 minus epsilon, then val plus is also bounded away from 1. It's 1 minus epsilon prime, let me say. Okay, and this is important because just together these two give me the parallel repetition, right? How do I get the parallel repetition from this? Let's just keep the picture. So this implies that if the value of h is bounded by 1 minus epsilon 0, let me call it 1 minus epsilon, then what is the value of h multiplied with itself k times? It's the value of h. Well, I think of this as h times h to the k minus 1. So it's the value val plus of h times the value of h to the k minus 1. Okay, and this is smaller than value plus of h squared times the value of h to the k minus 2, and you get the picture, right? So in the end, I get val plus of h to the k minus 1 times the value of h. So this is 1 minus epsilon prime to the k minus 1 times 1 minus epsilon. So it goes down exponentially with k. So that's why it's really enough to focus on two games. It's a stronger statement, in fact. So let's think again of this. Maybe I need the edge versus edge picture. Okay, I need yet another picture. I should have said it before. So for any think of a six coloring. So now let's think of, we're playing this edge versus edge game. Remember we had this 3-color graph, then we thought of the edges, and you can 6-color them. So what is a prover strategy? It's really a function mapping to each edge. Each edge gets a color 1 through 6. And if I want to now forget about the fact that it's edges, I just have, these vertices of E, of my graph H. So let's call H, X. Let's call the vertex set X, and the edge set, okay, I don't know. I don't need this so much. Then for every question in X, I have some answer. There is some answer in 1 to 6. Right, and I'm now also going to allow probabilistic answers. And so the way I think of a prover strategy, it's a collection of probabilities. Probability of A conditioned on X. For all X in X and all A in 6. So 6 is just happen to be 6. It can be any alphabet. Okay, so this is a prover strategy. This is a prover strategy. Yeah, and now let's think of how to express the fact that that the proof of strategy, that the value of the game in terms of these numbers. Okay, so notice that P A of x is non-zero, and that the sum of P A conditioned on x, sum over A, is exactly 1. Meaning for every question, there is a distribution over A's. Okay, so I have these two conditions. So any kind of any assignment of numbers PA conditioned on x that obeys these two numbers is a proof of strategy. Okay. Now, one way to think of it is that I have some kind of distribution. I have a random variable that says what is the question that I'm asking. So now let me call these x and x prime. Okay, and so the two questions are x and x prime. These are two random variables. And the two answers are also random variables. A is a deterministic function. Well, it can be a randomized function of x. Okay, so A is a random variable and A prime is a random variable. Now I can also think of, all right, so this is a collision game. So, the answer here, to understand if it's consistent with A prime, what I do is I project it to the common vertex. So I need to also think, okay, I have 5 minutes, so it's not quite optimal. Okay, so maybe it's not a good idea. Let me think what to do. Yeah, but as ambitious as I am, even 7 minutes will not be good. So let me think. All right. All right, okay, so let me just, okay. All right, so still a few minutes. I will be able to do something.
You can walk a bit faster.
Yeah, walk to French house. Friend's house or French house? House of France, okay. So we think of it this way, there was this vertex versus edge game that we built our symmetrized game on. So we chose some vertex V. It's too far away. Put them here. And then I chose, condition on V, I chose E and E prime. Okay? Let me call it, I chose some, okay, E and E prime. I stay with E and E prime. And this is the symmetrized picture. Okay, so I chose a random, the referee chose a random V and then chose two random neighbors. Okay, and then, these guys gave answers. So this guy answered A, and this guy answered A prime. And then you can see whether the answer A, what is its value when you project down to V. So, this gave some number like some color from 1 to 6, and it implied some color on the vertex V. So let's define this random variable B, which says what is the answer that E gave when you projected it down to V. Okay, so I'm sorry, I say it again. We have this game of choose a vertex and then choose a random edge and then choose maybe another random edge. Let's focus on the first step. Choose a vertex, choose a random edge. You get the answer, project it back to a color for the vertex. This is a random variable, call it B. Okay, similarly, you do it again. The edge is E prime, the answer is A prime, the random variable is, you can call it B prime. Doesn't matter. Okay, so if I get a collection of probabilities P of X, of A conditioned on X, I can also look at the probabilities P of okay, E is the question, right? So P of A conditioned on A. I can also look at the probabilities P of B conditioned on V. Okay, what is P of B conditioned on V? It's the probability of choosing V, choosing a random neighbor E, looking at the answer, projecting it back, and getting B. Okay, so it's just a bunch of probabilities. P of B conditioned on V. Okay, now what is the goal of the players in this game? The goal is that to be as consistent as possible, right? So, for example, if the vertex player gets V, the edge players get some E and E prime, their goal is to answer something that when you project it down is the same B. Okay, so it's like the more consistent they are, the better off they are. And indeed, if there's a perfect strategy, then for every V, PB conditioned on V will be 1 for a specific v, for a specific b, and 0 for all the other b's. Is this clear? Okay. So this is their goal, to be very consistent. Okay. But, you know, maybe the graph is not recolorable and they cannot do it. So it could be that for some of the v's, the distribution kind of goes between several different v's. And this is actually exactly the measure of success, because what is so suppose I chose some specific v, and now I choose e, and I look at its projection, and I get some b, and then I do it again independently, right? So I choose e prime independently, and I look at its projection, and I get b prime. Success is when b equals b prime. So how do you express this analytically? It's exactly the sum over all possible b of this probability b conditioned on v squared, right? Because it's like, you know, some fraction of these e's project down to b. And to project down twice to b is to exactly choose this fraction from this fraction twice. So it's exactly p of b, p bv squared. And summation over all b, because they need to agree. I don't care how they agree. So they can agree on b1 and b2. This is a sum over 3 values in this example. Okay, so the total expression for the value of the game is expectation over v, because what the referee is doing is first selecting v at random. So this is expectation over v. And then you want these collision probabilities of p, b conditioned on v. Okay, so what I tried to explain is that this is exactly the value of the game under the strategy P, A, E. Sorry for being so small. So as I said somewhere, that collection of these numbers is a strategy, and the value of this strategy is exactly given by this expression. And what's nice about this expression, if you write this out, like a long vector indexed by v and b, it's a vector, and this is a kind of a 2 norm. It's just a sum of squares of the entries of this vector. This is kind of very convenient to work with. Okay, so now I will say what the Chigger inequality.
So now we're doing relaxation. The original problem was 0, 1, and now we do real relaxation.
So far, I didn't do the relaxation.
Okay.
So what we came up with is that the value of the game is the supremum over all strategies P, A, E. Okay, and when I say strategies, I meant 2 conditions. One is that P, A, E must be non-negative, and the second is that summation over A of P, A, E is 1 for every E. Just saying that this is a probability distribution for every E. Okay, so it's the supremum over all possible such distributions of what? Of exactly that thing. Expectation over V, summation over B, P of BV squared, where this is missing from the notation that, you know, this is defined based on these distributions, using this kind of, you know, thinking of this as a random variable that is defined based on these random variables. Okay, so this is the value, the honest to God value. There is no relaxation. Now, what will be the relaxation? The relaxation will be the same thing, except you don't need, you just remove the requirement that they sum to 1. They can be less than 1. Okay, so you basically allow less than equal to 1 instead of 1. Seems like a very innocent relaxation. And this is the Valpla. So it's allowing strategies that abort. You know, like sometimes you just refuse to give an answer. Okay, so it's like, it's not a probability over all possible answers. You're also allowed to say abort or something like that. Okay? And the theorem that I wrote here is that turns out that, okay, so I'm cheating here. So I guess I should write divide by gamma. Like that, so. Okay. The point is, so there's 2 points. One is that if you have even a relaxed strategy that's too good, so if it was bigger than this number, then you could get from it a perfect strategy. But this is only conditioned on the graph being an expander. So this gamma is like the eigenvalue gap. The eigenvalue gap is very small, then this should be meaningless. I don't know if the gamma should be here, maybe. Okay.
Gamma you find, no?
Should it be like this, gamma like this? No, but I mean, it should not even be bounded from 1. Like, I don't know what to say. So, okay, let me just say, if G is expanding, in the normal sense, just this graph is an expander in the normal sense. Okay, and in case it's not an expander, there's a slightly more tricky definition you need to do in this relaxation. Definitely no time for that. I didn't intend it even. But okay, let me just tell you again, why is this like a Chigger inequality? A Chigger inequality says that if you have a labeling of the vertices by real numbers, such that like the quadratic form corresponding to the graph is big or it's small. I don't know. Depends if it's Laplacian or not. Then you can round it to a 0, 1 labeling, which has a similar value. Okay. So here it's the same kind of thing, except okay, here is the same kind of thing. Since I'm already stealing time, I'll not explain this any further. Yeah, let me just say, why does this even notion come up of like having probabilities that don't sum to 1? And the reason is that if you have a strategy, so what I'm now trying to explain is this theorem. Like, why does the fact that that this value is very big implies that this value is very big? Okay, so there is some sense in which you have value of h, and you want to say that when you multiply h by g, the value goes down. It's now value of h times val plus of g. But suppose it doesn't go down. Suppose the value of h is similar to the value of g times h. Okay, so then it means that there is a strategy for g times h that does too well. Okay, so you look at this strategy, and you find in it that if you condition on one of the questions in h, there is a strategy for g that does too well. But when you condition on one of these columns of h, the word conditioning is not correct. Really what you need to do is to condition and also request that the answer is something. And then what you end up with is not a strategy for g. You end up with this exact object where some of the probabilities don't sum to 1. And still you're able to derive a strategy. So, okay, this was way too ambitious to give this in 15 minutes. But, okay, this is what we have. So, thank you.
For the whole series, here is a little something.
Oh, wow. Thank you for inviting me, and also for inviting me to organize. And I think the king organizer is doing a fantastic job. So.